So now let's look at how to take integrals by partial fractions. First off, how do we do partial fractions? The idea for this is if I have a fraction, the first thing I'm going to do is factor the denominator. And then, so long as there are no repeated factors, I will write the fraction as the sum of fractions with the factors as denominators. I will multiply by the missing factors to sort of get what would be a common denominator. Solve the resulting system. And then finally, what this does is this breaks up a degree 2 or higher denominator into smaller degree denominators. Finally, I will actually be able to, in this case, take the integral. And most of the time, and I'll explain why when we get there, most of the time the integral is going to end up giving us natural logs. Sometimes if we have repeated factors in the denominator, I can actually get something a little bit different. But I'll show 4 examples working through that. This first problem is a sort of simple starting example. I look at the denominator, and in here I see that the denominator factors as x minus 2, x minus 5. And so let me do it this way. I'm going to want to make 2x plus 5 over x squared minus 7x plus 10 equal to the sum of fractions 1 over x minus 5 and the other over x minus 2. And what I'll do is to this fraction, I'll multiply the numerator and the denominator by x minus 2. And to this fraction, I'll multiply the numerator and denominator by x minus 5 because that would give me a common denominator. That common denominator would actually be x squared minus 7x plus 10. And so I will get 2x plus 5 over x squared minus 7x plus 10 equals ax minus 2a plus bx minus 5b all over x minus 5 times x minus 2 is x squared minus 7x plus 10. And I'll skip a few steps in the future. It's not great, but these problems will stretch on long enough if I don't. So in the future, I'm not going to end up writing these because I could multiply through by x squared minus 7x plus 10 to both sides, and for all intents and purposes, they will cancel out, of course, except where those are 0. I'm not going to write this on the top and bottom in the future. I'm just going to write it over here, but I am going to multiply it by top and bottom when I do this work. And so here's how partial fractions will work. I see 2x, ax, and bx, and that means that a plus b must equal 2. And I see the constant 5 and negative 2a and negative 5b, so these without the x have to add up, so negative 2a minus 5b equals 5, and I can just solve this system. Now, this system I'll do by hand. I'll show a calculator system in the next problem. To solve this by hand, I'll multiply the top by 2 to get 2a plus 2b equals 4. I will add straight down. The 2a's cancel. I'm left with negative 3b equals 9, which gets me b equals negative 3. And then I'll come back up. I'll use this first original equation and get that a plus negative 3 equals 2, and see that a equals 5. And that's all of the hard work for this problem. So now let's get the answer. Because a is 5 and b is negative 3, that means that I can rewrite this integral as the integral of 5 over x minus 5 plus negative 3 over x minus 2 dx. And if this were just 5 over x, I would get 5 natural log of x. I could do u substitution. I guess I'll show it. If I had this integral of 5 over x minus 5 dx, I could let u equal x minus 5, du equals dx, and I would end up getting the integral of 5 over u du, which is 5 natural log of the absolute value of u, which is, plus c, which is 5 natural log of the absolute value of x minus 5 plus c. So you see it works out nicely. As long as this is a coefficient of positive 1, I don't really have anything to worry about. It just ends up how I want it. Alright, let me get rid of all that mess, because I don't need this for the problem. So now I can look at this and see, okay, the antiderivative of 5 over x minus 5 is 5 natural log of the absolute value of x minus 5. The antiderivative of negative 3 over x minus 2 is minus 3 natural log of the absolute value of x minus 2. And then I have a plus c. And this is the answer that I like. I have seen on some AP tests, and I'm going to play a little bit loose and fast with the absolute values here, but I've seen them use the rules like 5 times natural log is the same thing as natural log of x minus 5 to the 5th, minus 3 times that is the natural log of x minus 2 to the 3rd, and then use the subtraction rule for logs to get the natural log of x minus 5 to the 5th over x minus 2 to the 3rd. I've seen this. I don't like it, but just know for the AP test, sometimes they will collapse this natural log expression. This is the answer I like. Alright, example 2. In here, the denominator is already factored, but there are a couple of problems, a couple of things that make this more difficult. First off, I have a quadratic up here, and I have 3 factors in the denominator, so I'm going to have to do a couple more things. I'm going to have to consider this, so I have a squared minus 2a plus 5 over all of that. Equals, and I'll have a over this little a plus 1, plus b over little a minus 2, plus c over little a plus 3. And the first problem is, this is missing 2 factors, missing a minus 2 and a plus 3. This is missing 2 factors, missing a plus 1 and a plus 3. And this is missing 2 factors, a plus 1 and a minus 2. If I multiply a minus 2 times a plus 3, I'll get a squared plus 3a minus 2a, which is the same thing as plus a, minus 6, which means I'll have a squared, plus 1a little a, minus 6 big A. In here, if I do a plus 1 times a plus 3, I will get a squared plus 4a plus 3. So I get ba squared plus 4ba plus 3b. And here, when I multiply a plus 1 times a minus 2, I get a squared minus a minus 2. So I'll get plus ca squared minus ca minus 2c. And that's all going to equal a squared minus 2a plus 5. When I go through and deal with all of the little a squareds, I'll get a squared. Sorry, let me just do it this way. A plus b plus c has to equal 1, because I have 1a squared there. When I look at all of the a to the first terms, I will get a plus 4b minus c equals negative 2. And when I look at all of the constant terms, I will get negative 6a plus 3b minus 2c is equal to 5. And this system is a system that could be solved by hand, but that's a little bit of a pain. Let me just do a quick review of how to solve systems in a calculator. If you have a newer calculator, there are some nice system-solving functions. The Nspires do it nicely. I believe the Casios do it nicely. But if you have an older TI calculator, probably the easiest way is to use matrices. So I'm going to come up with a coefficient matrix of the coefficients here. It is going to be 3 by 3 because I have 3 equations and 3 variables. So 3 by 3. The first row is all 1s because I have 1a, 1b, and 1c. The second row is going to be 1, 4, negative 1 because I have 1a, 4b, and negative 1c. And the last row is negative 6, 3, negative 2. So those are the coefficients. I'll quit out of this, make another matrix for the right-hand side. It is 3 tall and 1 wide, so 3 by 1. And it'll be 1, negative 2, 5. And because it's solving a matrix equation, I can actually solve the system by doing A inverse times B, which gives me that. Or if I like them in fraction form, which of course I do, gives me that. And so A is negative 4/3, B is 1/3, and C is 2. Let me write that down. A is negative 4/3, B is 1/3, and C is 2. So what all that means, what all that does for me is this. This integral is really the integral of negative 4/3 over a plus 1 plus 1/3 over a minus 2 plus 2 over a plus 3 dA. And I can do the antiderivatives the same way. So these will be the coefficients because I can factor them out. They are constants. And I'll get negative 4/3 times the natural log of the absolute value of a plus 1 plus 1/3 times the natural log of the absolute value of a minus 2 plus 2 times the natural log of the absolute value of a plus 3, all plus c. Now we have two special cases. Here's one of the special cases. What if the power up here is higher than the power down there? The first thing I have to do is actually reduce it down, divide it, because if I started off with partial fractions, I would get no r cubed or r squared terms. So I will do long division. I will put the denominator out here, r squared plus 3r plus 2. Put the numerator in here, 4r cubed minus 3r squared plus 2r minus 1, and divide it out. And so in here, how many times does r squared go into 4r cubed is 4r times. I multiply through. 4r times r squared is 4r cubed. 4r times 3r is 12r squared. 4r times 2 is 8r. And I subtract these. That cancels. I'm left with negative 15 r squared minus 6r. I'll bring down the minus 1. I do the same thing. How many times does r squared go into negative 15r squared? And that's negative 15 times. And I multiply back and get negative 15r squared minus 45r minus 30. And I subtract, so that means this is going to be addition, addition, and addition. Those cancel. And I'm left with, let's see, that's going to be 39r plus 29. And so I can do this. I can rewrite this here this here as the following integral. I can rewrite it as the integral of 4r minus 15 plus, I get this remainder, plus 39r plus 29 over r squared plus 3r plus 2. Okay. Now, in here, these terms are easy to antiderive. I'll hold off on that for a second until I take care of this. This one's harder. So I go through the process, factor the denominator, and I get r plus 2 times r plus 1. A over r plus 2 plus b over r plus 1. This needs an r plus 1 factor. This needs an r plus 2 factor. And so I get ar plus a plus br plus 2b. And that has to equal 39r plus 29. So I group them up and get a plus b equals 39. And group them up and get a plus 2b equals 29. And I'll solve it by hand. Subtract the 2 because those will cancel. I will get negative b equals 10. So b is equal to negative 10. And now substitute back in. I'll substitute in the first one. A minus 10 equals 39. So a equals 49. And so I can take this into my integral. I have the integral of 4r minus 15 plus 49 over r plus 2 plus negative 10 over r plus 1 dr. And antiderive. The antiderivative of 4r is 2r squared. The antiderivative of negative 15 is minus 15r. The antiderivative of 49 over r plus 2 is 49 natural log of the absolute value of r plus 2. The antiderivative of negative 10 over r plus 1 is minus 10 natural log of the absolute value of r plus 1 plus c. And finally, one more question. This one has a slightly different problem, and here's the problem. When I factor, the denominator is actually x minus 2 squared. And so the way to deal with this is the following. I'm going to write this as a over x minus 2 plus b over x minus 2 squared. It's still going to help because the problem with this problem is that I have an x and a 3 up here, and u substitution won't work because I cannot let u equal x squared minus 4x plus 4. It won't cancel out the numerator. But here, I'm not going to have any x's up here. I can do the work we saw earlier. So this is missing an x minus 2. This isn't missing anything. I don't need to bring it in. So I get ax minus 2a plus b, and that has to equal x plus 3. And I group it up, and I get a equals 1, because a and x. And I get negative 2a plus b equals 3, and that would mean that if a is 1, negative 2 times 1 plus b equals 3, b has to equal 5. And so I will get that this integral is equal to the integral of 1 over x minus 2 plus 5 over x minus 2 squared dx. This one's easy to solve. I know that that's going to be the natural log of the absolute value of x minus 2. This one's harder to solve, and here's how we do this. U substitution. I will let u equal x minus 2. That means du equals dx. And so I have the integral of 5 over u squared du, which is going to equal the integral of 5u to the negative second. The integral rule for a power function is I add 1 to the exponent and divide, so that's going to be, I guess I'll toss a plus c in there. It's going to be 5u to the negative first divided by negative 1, which reduces down to negative 5 over u is x minus 2. Okay, feel free to comment below with any questions. I hope this helped out.